All right, science bowlers, let's talk waves. All right, we get something that looks like this. This is the amplitude. This is an important quantity. We'll talk about it in a second. The distance between successive parts of a wave is a wavelength. And that's given the thing lambda. And then the frequency is the number of cycles per second, okay? We have this equation where that's the wavelength, that's the frequency, and this is the speed of the wave. And that only depends on the medium. So that kind of thing is that if you have a wave and then you change the frequency, this stays constant. And so however this is changing, you know, in the inverse way. There's another important quantity, and that's the period. The period is 1 over the frequency, right? So frequency is measured in hertz, and 1 over hertz is a second. Groovy. Interference. All right, we got 2 waves, and if they are in phase, that means the crests are right on top of each other, troughs are right on top of each other. Then you get constructive interference, which will look, if you're dealing with light, it'll look like a bright line, right? So you'll have things called interference patterns with some constructive interference and destructive interference. So bright and dark, bright and dark. So for light, it would be this. For sound, right, it would be loud. And that's because when these are in phase, right, say my amplitude is, 2 centimeters for both of them. Then I'll get, right, the amplitudes will add, and that's 4 centimeters. So amplitude is the thing that gets affected by interference. And amplitude gives you information about things being bright, things being loud, and the word that can be associated with both of those is intensity. And the intensity is proportional to the amplitude squared. Things like decibels is a measure of intensity, and it's got, whatever log stuff. Basically, if something's 1,000 times louder, then it's, right, there's 3 zeros and then you add a 0. So it's 30 decibels more if it's 1,000 times louder. So there's your, power of 10. And then that's that 3. Okay. Destructive, right, is where crest is on top of a trough, and then you get nothing. And this is called out of phase or 180 degrees out of phase. And that's destructive, so that'll be dark or no sound, depending on what kind of wave you're dealing with. Groovy. Just whipping through these papers. Let's talk more about the speed. So the speed of a wave, right, we said it depends on the medium. So what kind of media can we have? Light requires no medium, right? But it can travel through a medium, okay? And there we talk about a refractive index given by the letter n, and n equals 1 is the value in a vacuum, because the speed of light is c, which is your 3 times 10 to the 8th meters per second, divided by n. So in a vacuum, you get c for the speed of light. The speed of light in a material is always, that is beautiful writing. That says everything else. So the speed of light in a material is always greater than 1. And so that means that the speed of light is always less than the speed of light in a vacuum. Cool. Ooh, another fun fact about N. N is wavelength dependent, very slightly, right? So when you have prisms, right, and, oh, look, I have colors. I could use them. So red bends less, and purple bends more. And that's because the N is actually dependent on the wavelength. And so how do we know about any of this bending? This is something called Snell's law. So there's the normal to the surface. This thing has a value of index refraction of N1. This is N2. Whee! We've got a ray of light coming in here. This is the incident angle. This is the refracted angle. There's also the reflected angle. These are always equal, but these are related this way. And I know I just called that theta incident and theta refracted, but theta 1, theta 2 in this context. And so the ratio of those indices of refraction gives you sort of a relative bending, right? Because of that ratio of the signs of this angles. This is based on something called Fermat's, okay, my French is bad, Fermat principle. And that says that light picks the path to make sure that it takes the least time to get there. So that's something that you may or may not see. Is that what I wanted to say about light? What about the speed of sound and air? It is temperature dependent, right? Because it depends on, right, how fast those molecules are moving around. I think there's also a humidity dependence that I don't have like a formula for. But the temperature dependence is at least a well-known thing. 331 meters per second at T equals 0 Celsius. And then you get another 0.6 meters per second for every degree Celsius. Or obviously Kelvin. Okay. In the material, your speed is the square root of the bulk modulus divided by the density. I saw that in one of the problems, so I guess it's worth writing down. Cool. I'm going to pause right here.